Hello everyone, I'm Shohei Mori at Graz University of Technology. Today I'm presenting our work, Good Keyframes to Inpaint. Diminished reality is a conceptual counterpart of augmented reality. In other words, augmented reality adds more information to the user's perceived environment, but diminished reality deletes or reduces some part of the environment. To this end, diminished reality systems require reconstructing an occluded background to substitute it into the current view to cover the occluding object. Thus, the occluding object becomes invisible in our vision. Depending on available resources, we can categorize the methods into two types. One uses multi-view images and the other uses an inpainting technique. Our aim is related to the inpainting diminished reality system. Inpainting here refers to a process to collect pixels from the surrounding area of a region of interest to hide the region of interest with plausible pixel clusters, which is also known as exemplar-based image inpainting. Inpainting diminished reality systems often use a keyframe so that a single inpainted frame is reused in the subsequent frames. Keyframe inpainting helps keep coherent inpainted results over time or keep interactivity by updating inpainting results while showing the incomplete but ongoing inpainting process. If the keyframe inpainting results in good quality, then the system can guarantee the quality of the later frames. But if not, it keeps failing. Therefore, the user needs to select the keyframe carefully, but the question is how? Now we have multiple frames here, but can you tell which will inpaint the stuffed bear the best? Let's pick up 3 frames for brevity. In reality, the problem becomes a bit harder when it comes to a 3D scene inpainting. A system needs to inpaint both in color and depth domains. However, background reconstruction is often hidden from the user when the main application runs in color space. This is why we want a matrix that suggests which frame to select as a keyframe before running the inpainting. So far, the best solution is trial and error, unfortunately. So this is the goal of our research. So there are 3 sub-goals here. We introduce a metric for estimating the suitability of a keyframe for inpainting a certain region of interest. We introduce an importance ranking of our criteria, and we demonstrate how to best balance evaluation matrix. We also demonstrate the impact of the proposed approach on real application cases. We address this problem by defining and formulating heuristics in diminished reality keyframe selection, which I give you some more details in a minute. We calculate the best balancing weights for those heuristics. Our method is on the basis of the state-of-the-art diminished reality inpainting method for generic 3D scenes, Inpaint Fusion, which is also from a group. To this end, we define several areas in the camera field of view in color and depth space. That includes region of interest and its surrounding regions and so on. I am not getting into the details, but I try to cover the context due to the limited time. For the details, please refer to our paper. Please note that we focus on a single keyframe inpainting in this research because it's the minimal requirement and thus the most applications do so. Let's put this aside. So there are 6 rules, starting from rule 1. Keep region of interest fully inside. Inpainting algorithms find pixels from the surroundings area to fill in the region of interest. I will always show good and bad keyframe example here on the right for an easy comparison by visual. Without surrounding pixels, it is hard to connect smoothly the boundary to the other, or it needs to continue the inpainting of the first keyframe in the next frames or in additional keyframes, which requires some efforts to keep consistency over the frames. To complete a keyframe inpainting fully, we do not use a frame when the region of interest touches the boundary. Simply, we count pixels of region of interest that overlaps the boundary pixels. Rule 2. Secure source areas. When more pixel resources are given, it is easier to inpaint a region of interest. More pixel variations can omit noticeable repetition in the inpainted area. The best practice for this issue is to simply keep the distance from the target object in practice, but the system should tell that to the user. We measure how many pixels occupy in the field of view. Rule 3. Secure similar pixel resources. For better pixel connectivity, the system should guarantee that the scene contains similar colors in the near surrounding pixels and those in the far areas. In these bad examples, most of the region of interest touches the green carpet, but some parts touch the toy train. Then the majority wins, and the connection around the toy train part breaks. We calculate histogram correlations between the near and the far areas in color and normal maps. Rule 4. Minimize perspective distortion. Perspective distortion can easily break the inpainting since far pixels that show the same object smaller might be used to closer areas. This rule applies to systems that assume planar or near planar scenes. Therefore, in 3D inpainting systems, it might counterintuitively work, but or it actually does, as I will show you in our experimental results later. One may warp the image so that planes are rectified. However, this applies only to near plane scenes. We evaluate how many normal vectors face towards the camera backwards direction. Rule 5. Avoid depth discontinuity. The more occlusions will introduce more problems because depth in painting often assumes smooth geometric connections. We count depth discontinuity so that we can select our frame with less depth discontinuity. Finally, Rule 6. Reconstruct the scene fully. 3D inpainting relies on depth samples from the system. That is, the scene should contain enough number of depth pixels. Since users do not see the reconstruction running in the background, especially in applications showing the visible color space. Therefore, the system must internally know how many reconstructed pixels exist within the field of view. Now we have defined 5 rules or the metrics, and somehow we need to balance them to get the final metric score or value. To do this, we assume a linear combination of the criteria. Thus, our goal here is to calculate the weight, WK. To do this, we minimize the difference between the calculated score and our balanced score, and to find the weights. We use LPIPs to evaluate the plausibility of inpaint results. We create our own dataset to collect keyframes with variance in our measures and to avoid pathological examples. For the final weight, we average the scores of color and depth, but here let me show you the individual results. As a short summary, the rules for the size of region of interest and depth continuity have higher impact. The other rules with subtle weights have subtle weights, and this suggests difficulties of a keyframe selection, especially when the two major rules do not show differences over frames. For example, when the user keeps distance from the target object and the background depth is smooth enough. As I quickly explained before, the rule for normal directions has a negative impact in our 3D scene dataset. We conducted 2 experiments to evaluate our weights and the other 2 baseline approaches. First, we compare ours, WS here, with average weights approach AS. Namely, we set uniform weights to our system. We evaluate the probability of of how likely ours selects better keyframes than the averaged weight approach does as their best keyframes. Similarly, we evaluated the worst keyframes. We also evaluated ranking ability, which tells us how likely LPIP scores of AS and WS on their best keyframes are lower than those of their worst keyframes. The graphs on the right shows if the bar goes above the 50% or not, and ours is better than the averaged weight approach. In the second experiment, we compared our method with the averaged weight approach and random selections. Random selection means to randomly select frames in a video and check the quality of the inpainting as a novice user would do. Again, we evaluate the probability in videos with different lengths. The results show ours is over 50% probability in average. We also discuss standard deviations in a keyframe to show the stability of inpainting results from random sheets, but please refer to our paper for the details. We implemented 3 applications to demonstrate how people can apply our approach to their diminished reality systems. The first example is automatic keyframe selection, where the system can automatically select the best keyframe from previous frames. The second example is user navigation to guide the user to let them seek a better keyframe instead of selecting the best keyframe from the previous recorded frames. The third example is marker hiding, which is a popular application in diminished reality to virtually implement markerless tracking with a fiducial marker. In this case, we only apply 3 criteria. So this slide shows our contributions again and limitations and future work. Thank you for your attention.